So my name is David Litwin. I'm currently a postdoctoral researcher at GFZ Potsdam in Germany. I am coming there from Johns Hopkins University in the US. I'm American, which you might be able to tell from the way I say things. I'm really excited to be here, and thank you for having me to give this talk. And I think that several things in the last talk, especially the question that we had at first, are a good segue to what I'm going to be covering today. So I want you to first reframe your mind a little bit, because we're not going to be talking just about things that happen in observable time frames, but we're also going to be talking about things that happen in landscapes over really long time frames, into the realm of millions of years. So with that, I'll get started with a little bit about where I came from in my dissertation work, which was thinking about more at the hill slope scale, the interrelationship between runoff generation and the evolution of landscapes. And I kind of noticed, and many people have noticed, that there are some similarities to what goes on when you think across these timescales at hill slopes, which is that these hill slopes shed both water and sediment under the influence of gravity, according to some transport laws that may or may not be similar to each other. And they respond to changing forcing and boundary conditions. And the kind of interrelationship of these processes acting at the same kind of landscape scale suggests that there could be some link between the two of them. And I was interested in exploring that and the role of the subsurface in particular as a hydrological control on this relationship between landscape form and runoff generation. So we know that this structure of the critical zone of the subsurface, as we just said, affects where water goes. And canonically, you can think of this diagram by Tom Dunn from 1978, where he has three end members of runoff generation and a kind of relationship between those to both climate and vegetation and things like that, but also to the geomorphology of the landscape, the topography and the soils. And particularly, he describes this relationship between saturation excess, overland flow occurring in places with generally thin soils and gentle topography, and more subsurface flow path dominance in places that are steeper and have deeper, more permeable soils. So we've observed this a lot of times in the field, but the question is there some reason why that combination should exist in nature? Should it be more common than random configurations? Has to be this way, learning. So I took that idea and thought, okay, if we're really going to understand the evolution of landscapes, we probably need a model that can do both. So I have a hydrological model here that does all of the basic things you would expect a rainfall runoff model to do in a humid landscape. We generate storms, we have some simple vadose storage and recharge to a saturated zone. We simulate the water table dynamics, route water over the surface, and use that to get a temporally average field of effective discharge. And we send that to a landscape evolution model where it drives the fluvial component of erosion. Along with other kind of characteristic erosion and evolution processes at this small landscape or catchment scale, we evolve the topography and we send it back to the hydrological model as a boundary condition. And we keep doing this back and forth until the topography is in some sense in equilibrium with the hydrological function of the landscape. And kind of our core question in my dissertation was what exactly that equilibrium is and what it looks like. Because we have a lot of people who are modeling centric here, I thought I would just give you a little bit of a more sense of what this model does. It's pretty simple. It looks like some stuff that we talked about earlier this morning, where we have a shallow aquifer model using the Dupuy-Forchheimer assumptions, and we're routing it over the surface in kind of a steady state form, where we get seepage from our saturated zone, and we route that to calculate discharge downstream. We send that to the geomorphic model. This is, from a geomorphic perspective, slightly better than the vanilla or baseline model in the sense that we do have our discharge in the form of our fluvial erosion term, our hill slope diffusion term. Hill slope erosion term is like nonlinear diffusion. And we have some uplift or source term. And we're going to run this to steady state. And when we do that...
David, can I ask something?
Yeah.
Do you evolve the permeability at all?
Okay, so this is an important limitation.
Okay.
We decided to focus on the relationship between runoff generation and topography, adding in the subsurface evolution as well. I tried. At first, I really wanted to do that as well, but it turned out with just the basic rules, it was quite unstable to get a satisfying answer. So what we wound up doing is prescribing that weathering must always keep up with erosion so that we keep a fixed kind of permeable thickness, spatially uniform through time.
And no vegetation?
No explicit vegetation. The vegetation comes in a little bit in the sense that the Vadozone model is something that Kieran is actually deep into at the moment, where we have spatially different recharge to the saturated zone based on like a root uptake distribution, more or less. So we evolve this model towards some steady state, and we do see that subsurface properties and climate are really key to understanding the relationship between topography and runoff generation. So in my full talk, I would show you a whole bunch of these. I'm just going to show you a few. If we take a base case that looks something like this, and we increase the transmissivity relative to precipitation, you can see that we increase our hill slope length, and we decrease the size of our variably saturated areas in light blue. And this is effectively because we've increased the amount of water we can put through the subsurface before it emerges at the surface and has the potential to erode the landscape. We can also increase the water storage capacity relative to the depth of the storms. So do we have a bunch of small little storms and a lot of storage, or do we have big storms and not much potential storage? And when we do that, these small storms result in very little variable saturated areas and a slightly increased hill slope length because we've effectively lost that ability to expand the aquifer up onto the hill slopes, at least occasionally. So when you do this for a whole lot of cases, we find this emergent relationship that has some bearing, at least, on what Dunn originally observed, where we have this ratio of quick flow to base flow related to a dimensionless relief. So cases that are high relief tend to have more base flow, more subsurface flow pathways, and very little variably saturated area. Places that have low relief tend to have large variably saturated area, more done overland flow, like that diagram predicts.
Can I ask you a quick question?
Yeah.
Do you have an actual steady state, or is it more complicated than that?
It's more complicated than that. It's not a true steady state, but it's...
Can you give a quick insight into...
So, like, you know, any time that you have a stochastic set of storms that you're running, we would hope that the average that we use to erode is like a decent average over that distribution. But through time, you can get perturbations. The perturbations will most likely even themselves out. This kind of model likes to go to a fixed steady state when the hydrology is really simple. So it's not something that's going to, you know, keep moving the river network constantly through time or anything like that. But the precise dynamics of this are something that the landscape evolution community is still grappling with a little bit.
Around local minima because of the noise or something like that?
You can, like, you know, you can get incision of a channel that then fills up for a little while with sediment and hangs out, and then, you know, incisors again and things like that. Yeah. Okay, so that was my dissertation work. Now we're going to take this into an extreme example and do some really bad karst hydrogeology. And I apologize to people who do karst because we're going to butcher some things in the name of thinking about stuff on geomorphic and geologic time. So karst, of course, breaks lots of rules. And it's also really common in the world, so it's worth kind of understanding for that reason. From a hydrologic standpoint, 3 of the main rules that you can think of it breaking off the top of your head are it breaks watershed assumptions. Karst systems can move water across surface drainage divides with ease, with very small hydraulic gradients sometimes even. It breaks continuum assumptions because specific conduits often really matter in the porous media kind of block of limestone, and you can even have turbulent flow develop. And it also breaks some stationarity assumptions. So hydrologists, we usually like to think of our landscape as a relatively fixed canvas onto which we can do stuff. But this is, the evolution of a new conduit around a tunnel that they dug for a train. And they were saying that the karst system would make a new conduit around where they blocked it in about 100 to 200 years. From a geomorphic standpoint, we also know that it breaks some important rules. So this may be a little bit less familiar to you, but when geomorphologists think about landscape evolution, we might think about adjustment to base level in 2 different watersheds that share a drainage divide, where if this watershed is cutting down, it's going to push its drainage divide toward the one that isn't cutting down as quickly, and we'll lose drainage area over on this side. But, and that's driven by the fact that we have water doing erosion up in these headwaters. And we see that in landscapes all the time. But in a karst landscape, you can have situations where you actually capture that drainage area without having to move the divide at all. So that's a really kind of key difference there that is going to affect the dynamics and potentially stall how landscapes evolve over a long time and how they respond to tectonic signals that move through landscapes. So in that respect, I'm going to give you a little perceptual model of the competing processes that might lead to the birth, persistence, and death of karst landscapes, and think a little bit about their long-term evolution with a little bit of introduction to start with. And I can move a little bit quickly since I know we're getting toward dinner and already over time. So I'm not a geochemist at all, but there is one key feature of the geochemistry of carbonate dissolution that's really important for us. So this is calcium carbonate, and its dissolution rate can be described by some power law function like this, and the kind of key feature has to do with this exponent n. So if the exponent was 1, we would have first order kinetics, and in short, water going into a fracture in limestone would saturate with our key ions very close to the surface, and basically no more reactions would happen as you got further into the rock. But that's not what happens. As you get closer to your equilibrium concentration, we wind up in higher order kinetics, so we maintain some concentration that's below the equilibrium far into a fracture, and that allows us to keep dissolving things far into the rock. And that's why karst landscapes do different things than weathering in basalt or something like that. And obviously this is super simplified, there's a lot more complexity to it. But if you combine all these factors with mass balance and some relationship between hydraulic head and flow, you can solve for how a conduit will evolve through time, and you get something super nonlinear, with the key feature being that early in time, we have really low flow rates through an evolving conduit or fracture to begin with, and then at a certain time, called the breakthrough time, we see a massive increase in flow rate that corresponds to the opening of this whole conduit system. And people have taken this much further. They've done it in 2 dimensions and looked at systems of conduits, and even looked in 3 dimensions at whole kind of karst aquifer evolution. But these are really challenging models to run and hard to do over really long time scales that we would need to think about responding to tectonic forces. And another kind of key feature of them that's a little bit frustrating has to do with another dynamic of karst itself, which is that it's really sensitive to its initial conditions. So you can see this is the breakthrough time here, t. It has in it a0, the initial fracture width, to the -3. So we have 6 orders of magnitude difference in that breakthrough time, with just 2 orders of magnitude in the initial fracture width, which is wild. And it's also sensitive to our model formulation, like we were talking before. If you have exchange between the conduit and the matrix, you can wind up with another 2 or 3 orders of magnitude difference in how long this thing takes to evolve. So I thought, okay, well, we could do something really fancy like this, but we still have this massive uncertainty in what's actually going to happen. So why don't we do something more simple, go back to the real basics with a kind of bulk or effective porous media approach, which, despite the fact that there are some clear limitations to doing that in karst, people have been doing it and at least conceptualizing karst in this way for quite a while. So here's the relationship between the equivalent pore diameter and the porosity, and they've kind of drawn out this area which has relatively low porosity relative to the equivalent pore diameter, which is kind of characteristic of karst features. We have different origin rocks that sit maybe outside of that zone, or their fractured equivalents in the dashed lines could be in it already, and then we'll see further evolution in this through time as the system dissolves. And this is related in kind of some standard ways that we covered a little bit this morning. The hydraulic conductivity can be derived, these lines, from the equivalent pore diameter, porosity, tortuosity, a few other factors. So I thought, yeah, of course, ironic that we're doing this in a system that is not a continuum at all, but we got to do something, so this is what we're going to do. I thought, in the sense of the aquifer evolution, maybe we can take that kind of diagram and conceptualize our evolution as a parametric curve that moves through that space. So I just kind of used the theory as a basis to get a parametric curve, and then we move through it at a relation using a logistic curve, which is meant to model the fact that we have this sharp time at which the system really changes, which is the breakthrough time, and then also kind of a slowing of continued evolution associated with the change in boundary conditions from constant flow to, or from constant head to constant flow as the conduits open wide. I'm going to make a bit of a jump here, and now we're going to go back to geomorphology, and we're going to talk a little bit about what might happen to a limestone sitting on a basement that gets uplifted in a very kind of conceptual sense. So imagine we have some inception or initial exposure of that limestone unit. Our first circumstance that we can imagine is a case where we have erosion before the karst even gets established. And we can think of this in terms of timescales. If B is the thickness of our massive flat limestone unit up here, B divided by our erosion rate before the breakthrough time, when the porosity and hydraulic conductivity are pretty low, has to be less than our breakthrough time to get something like this. So we're conceptualizing that erosion rate before the breakthrough time as predominantly physical erosion, and the denudation rate after that time is maybe predominantly chemical, although we can talk about some nuances to that. We can also, of course, get past that initial phase and get karst establishment. So this is getting past the breakthrough time before we erode the whole unit away. And if we do that, one possible thing that might happen is that we get a scarp developing, and we can get removal by that scarp before we get more denudation of the surface that would remove it by kind of lowering the limestone unit. And in that sense, the relevant time scale is the width of the limestone unit this way, divided by the scarp retreat rate relative to the thickness and how fast you can lower it. If surface denudation exceeds any removal at a scarp, if a scarp develops at all, we could also imagine something where basically we lose it via chemical erosion. And what exactly that looks like is a little bit of an open question. I'm not going to try to answer that in too much detail today, but it's something that we need to explore a little bit further. And lastly, there's a case where we get stalled erosion or even reburial of the unit because of the tectonic setting or changing climate, etc., etc. So this is really highly simplified, but it's at least giving us a framework to think about how these landscapes might exist and respond to tectonic and climatic forces. So if we can encapsulate these in a model, again, we're going to do some heresy and conceptualize this karstified limestone unit as an effective porous media with that bulk evolution as I described before. And otherwise, we're going to use a lot of the same components that I described in my previous model. The main difference that now we also have some chemical denudation, which for the moment we're going to say is just uniformly able to lower the surface. And I have some weathered basement here as kind of a representation of our critical zone in places where we don't have karst. So I'm going to show you a bunch of figures that looked kind of like this. We have 4 different subplots. The first one is showing the local discharge, the local runoff produced on limestone in the green colors and basement in the blue colors. So the color is a way to tell which kind of unit we are on. This is going to be an oblique view of topography. This shows that parametric curve that I just kind of plunked in there to describe the evolution of porosity and hydraulic conductivity. And on this curve, we have both the fraction of limestone that's exposed on this area and the emergent relief of the landscape. So this first case here is going to be erosion before karst establishment. If we run this forward, I'll just go until the breakthrough time. And you can see already our limestone in the green, it's mostly gone. It's just a little bit of fractions kind of up at the headwaters as the signal of erosion moves from our boundaries here and here towards our water divide in the middle. And all that's happening before the breakthrough time of karst, as we described before. And we've pretty much removed our limestone. Good. If we go a little bit further through the breakthrough time, you can see we've massively increased the hydraulic conductivity. And as a result, we get some small areas that do develop more relief because they no longer have surface runoff right near the ridge. And you can see them down there. Aha. And it causes a little bit of a bump change in the relief, and we also slow down for a minute our loss of the limestone unit. But ultimately, this thing is fairly doomed, and it will disappear and will return to some kind of equilibrium fluvial topography. Now, a scarp retreat case. This one is a little bit more interesting. Again, we'll go toward the breakthrough time. And this time, the breakthrough is a little bit later, but we've still developed some kind of stream channels on both sides that are starting to get into our basement layer, but have predominantly limestone in their headwaters. And you can see they are darker blue and green, so they're concentrating groundwater from their surroundings and pulling it out towards the water divide, or towards the model boundaries. And yeah.
What is the breakthrough time here? This is millions of years, right? This is 500 million years, 500,000 years.
Yeah.
So breakthrough time here meaning that there'll be no more runoff?
The breakthrough time is the time until we massively increase the hydraulic conductivity.
Yeah, but that implies no more surface runoff.
Effectively, no more surface runoff on the limestone.
Yeah.
Which is what we see. Like, limestone features, despite being super soluble, stick around on landscapes for a really long time, and they form large relief. So, and part of the reason why they do that is because they don't effectively erode.
And so the water that is intercepted on the surface is, in your model, is magically removed from the landscape.
It goes to our shallow aquifer, and then it'll form seepage at...
But we don't see it here in this...
Not yet.
Okay.
1 second. Okay, so we're going to go through the breakthrough. And you can see, yep, we are no longer having any runoff on this surface. We've got these incised channel heads here. All right, but what's going to happen now in the future? We've kind of stalled our loss of the limestone layer. Yeah, we've got that starting to get exposed. But as we keep evolving from here, we have all this drainage area still up here collecting water, recharging it to the aquifer in the limestone that will have to exfiltrate at our incised channel network. So this channel network is going to grow. So these channel heads, in the seepage erosion sense of Alan Howard and Laity Malin and all these kind of papers from the 1990s, will first widen. And in this first step, they seem to not progress too far. And then eventually the channel heads will progress as well. I think this looks a little bit like what you see at Swabian Alb, where all of this is limestone up here, and you get this highly crenulated surface kind of near the edge. Maybe you could compare it to this, although, you know, highly theoretical little model here. And with further time evolution, you can see these channel heads propagating, seeping water and eroding toward our drainage divide and ultimately removing the whole unit. So that's kind of a very simple way of conceptualizing it, at least in this case. The third case is erosion by surface chemical denudation. So this, we're imagining a climate that's really active. We're going to have a really early breakthrough time, and we're also going to have the surface kind of limestone unit thinning because it's getting dissolved even at the surface. And I'm not going to go through this one in much detail because I'm a little bit skeptical of these results still. I only did this very recently, and you know, the significance we can talk about more later if you're interested. But until the breakthrough time, we kind of get this early breakthrough that leaves us with very little channel network developed before we lose our surface runoff, most places. Water table is still reaching the surface up in the middle, so that's doing something. But minimal relief, we still have all of our limestone on the surface. If we go to the next time and past breakthrough, you can see that the area experiencing surface runoff is actually increasing in the middle because the aquifer has thinned significantly, so its transmissivity is lower. We still haven't lost much of the limestone layer, but now, wait for it, it's very quick to see. All of a sudden, we're going to lose the whole thing. So I can maybe try to replay this for you again. We've incised, we start to develop drainage, and then the limestone layer is completely gone. And this is important. We wind up with a large, high plateau that is all of a sudden super erodible. So the next thing that happens is that whole thing is going to massively decay back to the equilibrium fluvial topography. So whether this is actually how it would go down, that's another question, but it gives us an idea of what happens when these limestone layers are persistent and then removed on landscapes. You know, death need not come so soon. This is something that we do see in real landscapes, where if you do have just a thin limestone layer up at the surface, if it's well drained, it can support huge amounts of relief. And we see this in places like the Rio Grande Rift, function and landscape form. We can get these positive feedbacks in karst evolution that yield a strong sensitivity to initial conditions. And I've tried to kind of see past all that complexity and conceptualize karst evolution using these trajectories in an effective porous media, where the time to breakthrough is a really key control on what is going to happen. There's lots more to do here. I'll give a quick comment on the karst project before I wrap up, which is that the reason why, or one of the reasons why we're interested in looking at this is because some of our collaborators at the University of Tübingen are responsible for the geomorphic component of the plan to locate a permanent home for nuclear waste in Germany. And one of the conceptual, possible sites is actually in the Swabian Alb, under the karst, in a clay-rich unit that's down there. And one of the key questions is, how quickly are we going to change the topography in that region? What region, and what does that mean for the long-term exhumation of our nuclear waste? So obviously we're just one really small component of that story, but you can't really answer that question without thinking about what the karst is doing. So with that, I'll thank you for listening, and I'll take any questions. I don't have my collaborators on here. My postdoc supervisor, Luca Malatesta, has been central to this work. And for my dissertation work, I should thank Kieran Harmon, Greg Tucker, and Katie Barnhart. Yeah.
Ready?
Yeah.
So I was curious, I was hung up on the whole landscape evolution thing from the beginning, thinking about the role of the statistics of things like rainfall.
Yeah.
So for example, storm events, they're not always Poisson, right? Like they don't always come at a nice rate.
Yeah.
So I'm wondering, these kinds of equilibria, how much do they care about power law statistics in strong rainfall? And also whether this is relevant at the scales that are relevant for this kind of thing, right? So,
Yeah. I think they are potentially relevant, but there's a kind of older concept in geomorphology that goes back to Red Swolman and some other people about what is the geomorphically effective event, and it's this trade-off, right, between the frequent events that are low intensity that don't do much, and the really big events that have the potential to do a lot, but are so infrequent that they might not matter that much. So you might think that there is some middle ground. In the fluvial geomorphology literature, they would call that the bankful discharge, right? Like, what's the discharge that your channel width and channel profile is adjusted to? But I think there probably are some landscapes where they could be really dramatically changed by large events, and where that might push them in a different direction. Especially once you start thinking about landscapes where those large events are not just doing fluvial erosion, but they're landslide driving, and they're doing other things that will affect a whole cascade of other processes.
very quick follow-up for what you were doing. You had Poisson-style statistics?
Yeah, Poisson-style statistics for this. Yeah. Yeah.
These models are really fun, and I wonder, has anyone tried to do physical modeling? Because I feel like the last decade or so, 2 decades even, has seen a rejuvenation in physical models.
Mm-hmm. Mm-hmm.
And I wonder, have you seen anyone try to represent this process?
Of karst or of other things? Of the landscape evolution.
Generally, right now, with the landscape geomorphologists and also hydrology, like there's so many cool scaled models out there for all kinds of things. Like for me doing hydric or thinking about flumes, but I've seen cool landscape evolution models at the scale of like half a room or smaller even.
Yeah, yeah.
Are you aware of anyone trying to work with karst-like materials that dissolve on time scales faster than they are necessarily physically eroded to try to play with some of these scaling relationships in a physical model that doesn't have to be parameterized with physics that I hear the like pain in your voice when you're describing the like physics you want to include that you're currently not including, right?
Yeah.
And I mean that in the fondest way, you know.
Yeah.
Sympathize as a modeler, but I just wonder, like, aware of things out there that are workflows for doing this with physical models.
I don't know of physical models for the karst stuff. I haven't looked too far into it, but I do have a recollection of some early people trying to do this. And we definitely know that there are things that will form karst-like features on shorter timescales, like evaporates are a key example. Like gypsum, you can watch that dissolve.
Or like salt.
Or salt. Yeah. Although salt, I'm not sure how the kinetics would work, whether you would get this like far propagation of conduits versus just like dissolution on site.
Or sugar, I don't know. Like,
Yeah.
Like I've seen people do really cool things with different materials to do scale landscape evolution models.
Yeah. Well, maybe I'll add that to my list of future projects. Yeah.
A key assumption in these landscape evolution models was the occurrence, guaranteed occurrence of a breakthrough event.
Yeah.
Meaning, and so, how comfortable are you with this central assumption? Because it defines almost everything what happens after that.
That you would get there at all?
Yeah.
So this is kind of a strange thing. The theory suggests that it's not hard to wind up with a circumstance where it takes 10 to the 9th years to get a breakthrough.
Yeah, but it's not 10 to the 9th that you're working with.
Yeah. But in the field, we see that these breakthroughs happen again and again and again.
Climate, but you're talking about a million years. There'll be many glacial cycles in between and whatnot.
Yeah. So that's another thing that I didn't really address here, is that if you talk to the karst people, they're often thinking about karst in a stratigraphy sense, where the breakthrough isn't one and done. It's you have a base level and you have some lag time until a breakthrough, and then you get karst developed at that level, pretty much at the water table elevation, and then you get base level fall. And you have to wait again until you get another breakthrough, and you'll wind up with another cave system. And you can wind up with cases where you have, on the Danube and other places, you have karst stratigraphy that records the history of base level fall. And it's pretty remarkable that despite all the complexity, these breakthroughs do happen in 10,000 years, or less than glacial to interglacial cycles. Kentucky in the US, the Mammoth Cave system is like 12,000 years old. And that's huge.
Yeah.
So, yeah.
Okay.
Thank you very much.
Yeah.